Hello everyone, and welcome. I'm excited to have you here today. Our presentation is titled, Understanding and Addressing Failure Modes in Supervised Learning, and the subtitle highlights how we move from common issues like overfitting and underfitting to techniques such as regularization and model evaluation. Over the next few slides, we'll explore these concepts in detail, with practical insights on how to improve your models. So, let's get started. Let's take a closer look at understanding and addressing failure modes in supervised learning. First, overfitting happens when a model becomes too complex. It ends up fitting the training data perfectly, but then struggles to perform well on new, unseen data. This means the model performs great during training, but doesn't generalize, which is a big problem. A common cause of overfitting is using overly complex models, like high-degree polynomials in regression. For example, if we use a very high-degree polynomial, it can produce those wild, wiggly curves that fit the training points exactly but fail to predict new data accurately. Now, in contrast, underfitting occurs when the model is too simple. It can't really capture the underlying patterns in the data, so it performs poorly even on the training set. This happens when we use models that are too simplistic, like low-degree polynomials in regression. Think about a linear or low-degree polynomial that just can't grasp the complexity of the data. It results in a model that doesn't learn enough. Understanding these failure modes, overfitting and underfitting, is essential because they directly impact how well our models will perform in real-world scenarios. Our goal is to find that sweet spot where the model is complex enough to capture the true patterns, but not so complex that it just memorizes the training data. Let's delve into understanding and addressing failure modes in supervised learning. First, when we evaluate our models, we need to use separate datasets. We typically split our data into a training set, which we use to fit or train the model, and a holdout or validation set, which is reserved for evaluation. This separation is crucial because it helps us assess the model's performance without bias, giving us a more honest picture of how it might perform on new, unseen data. Next, we rely on performance metrics to quantify how well our models are doing. For regression tasks, we might use mean squared error, or MSE, which measures the average squared difference between predicted and actual values. For classification problems, accuracy is a common metric, indicating the proportion of correct predictions. These metrics are really useful because they allow us to compare different models in a standardized way. Now, let's talk about overfitting and underfitting, which are common failure modes. Overfitting happens when our model learns the training data too well, capturing noise along with the true pattern. You can tell it's overfitting when the training error is low, but the error on the holdout set is high. Underfitting, on the other hand, occurs when the model is too simple to capture the underlying data structure, resulting in high errors on both training and validation sets. Recognizing these issues highlights why balancing model complexity and data representation is so important. To diagnose these problems, we can visualize how well the model fits the data and calculate the holdout mean squared error. These quantitative diagnostics guide us in making targeted improvements, helping us develop more reliable models. By understanding these failure modes and applying proper evaluation techniques, we can significantly enhance the robustness of our supervised learning models and ensure they generalize well to new data. Understanding how different failure modes impact supervised learning is crucial for building robust models. On this slide, we're focusing on the importance of properly understanding and addressing these failure modes throughout the development process. Let's start with dataset types in machine learning. Typically, we work with three kinds of datasets: the training set, the development set, and the test set. Each of these plays a distinct role. The training set is where we fit our model, adjusting parameters to match the data. The development set is used for tuning hyperparameters and making decisions about the model's architecture. And finally, the test set provides an unbiased evaluation of how our model performs on unseen data. Now, an important part of the workflow is the iterative process. We train on the training set, then evaluate on the development set. This back and forth allows us to refine the model, tune hyperparameters, and select the best version. It's a continuous cycle aimed at improving performance without overfitting. Next, let's talk about the role of the test set. This dataset should be reserved exclusively for the final evaluation. Once we've finalized our model after all tuning, we run it on the test set to get an unbiased estimate of its true performance. It's the ultimate check to ensure our model generalizes well. Finally, proper dataset splitting is fundamental. Ensuring that the datasets are split correctly helps maintain distributional consistency across them, which means the data in each set should represent the same underlying distribution. It also guarantees that each set is large enough for reliable and meaningful evaluation. All these concepts form a framework for applying supervised learning effectively. By understanding and addressing failure modes through careful dataset management and iterative improvement, we can develop models that are both accurate and reliable in real-world scenarios. Let's talk about understanding and addressing failure modes in supervised learning. One key point is that a highly expressive model, like a degree 20 polynomial, can fit the training data perfectly, but that doesn't mean it will perform well on new, unseen data. In fact, this often leads to poor generalization. When a model is too complex, it tends to capture not just the true underlying pattern, but also the noise in the data. This is known as overfitting. Overfitting can cause large errors when we test the model on fresh data, which defeats the purpose of building a predictive model. It's important to recognize that balancing model complexity is crucial for better generalization. A model that's too simple, on the other hand, may fail to capture the underlying data patterns altogether. For example, a linear model might be too simplistic if the true relationship is more complex. This results in underfitting, where the model performs poorly on both the training data and new data because it can't adequately represent the underlying structure. So the key takeaway here is that selecting the right level of model complexity is vital. We want a model that's expressive enough to learn the true patterns, but not so complex that it starts to memorize noise. This balance helps us achieve better performance and more reliable predictions across different datasets. Let's dive into understanding regularization. Essentially, regularization is a technique we use to prevent overfitting, which happens when our model becomes too complex and starts capturing noise rather than the true pattern. By penalizing this complexity during training, regularization helps our models generalize better to unseen data. Now, the key idea here is that we want our models to be as simple as possible while still fitting the data well. This balance is achieved through what we call the regularization term. When we set our learning objective, we don't just minimize the loss, we add a penalty for complexity. This penalty is scaled by a parameter called lambda, or lambda. Lambda controls how strong the penalty is. If lambda is high, it encourages the model to keep things simple by discouraging overly complex solutions. Conversely, a lower lambda allows for more complexity, which might be useful in some cases but risks overfitting. Ultimately, regularization nudges our models towards simpler, more generalizable solutions. This means they perform better not only on the training data, but also on new, unseen data. So, understanding and tuning regularization is crucial for building robust, supervised learning models that stand the test of real-world application. Let's delve into understanding and addressing failure modes in supervised learning, starting with L2 regularization, also known as ridge regression. This technique impacts model weights by shrinking them towards zero, which is crucial because it helps strike a balance between creating a model that is too complex and one that is too simple. By doing this, we prevent overfitting and improve generalization. When applying L2 regularization in polynomial regression, it acts as a smoothing factor. Instead of allowing the model to wildly oscillate, especially with high-degree polynomials, it encourages a smoother, more stable fit. This results in a model that captures the underlying trend without chasing every little fluctuation in the data. For linear models, there's an elegant analytical solution. Instead of iterative methods, we can derive the optimal weights using a modified version of the normal equations. The formula is theta star equals the inverse of x transpose x plus lambda times the identity matrix, multiplied by x transpose, why this straightforward adjustment ensures regularization is embedded directly into the solution. Mathematically, the cost function with L2 regularization includes a penalty term. It looks like J of theta equals the average loss across all data points plus lambda times the squared norm of theta. This means the weights are shrunk towards zero, but as a rule, they rarely become exactly zero, unlike some other regularization techniques. To define L2 regularization clearly, it adds a penalty proportional to the squared magnitude of the model parameters. This is a simple but powerful way to reduce model complexity, helping us prevent overfitting and improve the model's ability to generalize to unseen data. Overall, it's a key tool in our arsenal for building more robust supervised learning models. Let's take a closer look at understanding and addressing failure modes in supervised learning, focusing on the role of lambda, or lambda, in regularization. Lambda is a hyperparameter that controls how strong our regularization is. Essentially, it influences the balance between making our model complex enough to fit the data well and keeping it simple enough to generalize to new, unseen data. Now, if lambda is too small, the penalty it applies to model complexity is quite weak. This can cause our model to overfit, meaning it performs really well on our training data, but struggles with new data. Overfitting is a common failure mode, and regularization helps us prevent that. On the other hand, if lambda is too large, we impose a very strong penalty on complexity. This can lead to underfitting, where the model is too simple to capture the underlying patterns in the data. So, choosing the right value of lambda is crucial. We usually select this value through a process called hyperparameter search, typically using a development set. Our goal is to find the lambda that offers the best holdout performance, which means balancing bias and variance for optimal generalization. In summary, selecting the appropriate regularization parameter lambda is key to building robust models that neither overfit nor underfit, ensuring better performance on unseen data. Let's take a closer look at understanding and addressing failure modes in supervised learning through the lens of L1 regularization. First, what exactly is L1 regularization? Well, it's a technique that penalizes the sum of the absolute values of the parameters, which is expressed mathematically as J of theta equals the average loss plus lambda times the L1 norm of theta. This approach is often called the lasso, and one of its key features is that it encourages sparsity in the model. In other words, it tends to push many weights to exactly zero, effectively removing less important features from the model. Now, how does this differ from other regularization methods? Unlike L2 regularization, which shrinks weights but rarely to zero, L1 performs an implicit form of feature selection. This simplifies the model by excluding irrelevant or redundant features, making the results more interpretable, something that's especially valuable when dealing with complex datasets. When it comes to optimizing models with L1 regularization, it requires specific iterative algorithms. Common techniques include coordinate descent and least angle regression, both of which are designed to efficiently handle the non-differentiability at zero caused by the absolute value penalty. The sparsity induced by L1 regularization has a significant impact. It leads to more compact models, which are not only easier to interpret, but also computationally more efficient. This is particularly useful in high-dimensional datasets, where reducing complexity can make a big difference in performance and understanding. So, to sum up, L1 regularization, or the lasso, is a powerful tool in our supervised learning toolkit. It helps us create simpler, more interpretable models by selecting features automatically and reducing overfitting, especially when working with large, complex datasets. Understanding and addressing failure modes in supervised learning is crucial for building robust models. Today, I want to focus on sparsity and its benefits. So, what exactly do we mean by sparsity? Well, sparsity refers to the idea that many of the model's parameters are exactly zero. This might sound simple, but it has some powerful implications. When most parameters are zero, the model is essentially focusing on a small subset of important features, which makes it much easier to interpret. Instead of getting lost in a sea of weights, you can see clearly which features matter most. Now, another key benefit of sparsity is computational efficiency. When the model ignores features with zero weights, it saves a lot of memory and processing power. This means faster training times and more efficient predictions, especially with large datasets. To make this more concrete, let's look at some visualizations from the diabetes dataset. With ridge regression, you'll notice that the weights shrink gradually, but don't quite hit zero. They just become smaller. On the other hand, with lasso regression, the weights not only shrink but actually hit zero, effectively removing those features from the model. This visual difference really highlights how sparsity works in practice. In summary, sparsity helps us create models that are both easier to interpret and more efficient to run. It's a powerful tool for addressing some of the common failure modes we see in supervised learning. Let's take a closer look at understanding and addressing failure modes in supervised learning, specifically through regularization techniques. First, with L2 regularization, we can think of it as constraining the parameters within a round ball. This shape is important because it makes sparse solutions, where some parameters are exactly zero, less likely to occur. The round ball essentially treats all parameters equally, which means it doesn't favor solutions where some are zero. That's why L2 regularization is great for controlling overfitting, but it doesn't naturally lead to sparse models. Now, shifting gears to L1 regularization, the intuition here is quite different. L1 constrains the parameters within a diamond-shaped region. This shape is crucial because its corners align with the axes, meaning solutions tend to land at these corners, where some parameters are exactly zero. This geometric property is what makes L1 regularization effective at inducing sparsity in models. So, to connect everything back to the overall theme, understanding these geometric constraints helps us see why certain regularization methods promote sparsity, while others do not. It's all about the shape of these constraint regions and how solutions tend to settle at specific points within them. Understanding and addressing failure modes in supervised learning requires us to grasp some key assumptions. First, we assume that the data we use is sampled independently and identically distributed, or IID, from a fixed data distribution, which we call P. This assumption is crucial because it ensures that our training data and evaluation data come from the same underlying distribution, making our performance estimates meaningful. Next, let's talk about the role of the holdout dataset. This dataset is also IID from P, but is distinct from our training data. We use it to evaluate how well our model generalizes to new, unseen data. Essentially, it acts as a benchmark, giving us an honest measure of our model's performance in real-world scenarios. Now, defining what makes a good model hinges on its performance on this holdout set. We select a metric, like accuracy or mean squared error, that provides a standardized way to assess success. A good model is one that performs well according to this metric, meaning it generalizes effectively beyond just the training data. Finally, the size of the holdout set matters a lot. If it's large enough, it gives us a reliable estimate of how our model will perform on new data from the same distribution P. This reduces the risk of overfitting, where our model might perform well on training data but poorly elsewhere. All these points tie back into why supervised learning works. The core assumptions about data sampling and evaluation are what allow us to build models that generalize and perform reliably in real-world applications. All right, let's delve into understanding how we can address failure modes in supervised learning through this proof. The key idea here is that machine learning can be proven to work under certain conditions, and this slide highlights the main components of that proof. First, we have the accuracy gap, represented by epsilon. This epsilon essentially quantifies how much our model's accuracy could potentially differ from perfect accuracy. The smaller epsilon is, the closer we are to achieving optimal performance. Next, we assume a finite model class, which we denote as M, containing H models. This is important because having a finite set allows us to analyze the probability of selecting an inaccurate model more precisely. Then, we consider the training data size, Denoted as n, the crucial point here is that as we increase n, the amount of data we use for training, the probability that our learning algorithm produces an inaccurate model decreases exponentially. Specifically, it diminishes at a rate proportional to 1 minus epsilon raised to the power of n. This exponential decrease is the core insight. It tells us that with more data, the likelihood of failure drops rapidly. So, in practical terms, if we keep increasing our training data, we can make the chance of choosing a less accurate model arbitrarily small. Overall, this slide encapsulates why having sufficient data and understanding the model class size are fundamental to ensuring reliable machine learning performance. It ties back to our broader goal of building models that are both accurate and dependable, especially as we scale up our data collection efforts.